Hello students, welcome to EPG Pathshala and I am Reema Gupta from University of Delhi. Today students, we are going to discuss about the module that is Electrical and Magnetic Properties Part 9. So, it is from the paper Ceramics. So students, let us see what we are going to learn in this module. So students, we will be first discussing about the basis of magnetism in materials. Then we will be discussing about the various types of magnetic material like diamagnetism, paramagnetism, ferromagnetism and ferrimagnetism. Then we should discuss about the switching in ferromagnetic material. Then we will be moving towards magnetostriction, ferromagnetic and ferrimagnetic materials, their magnetic ferrites and applications. So before moving further, let us discuss about magnetism. So magnetism is a class of physical phenomena that are mediated by the magnetic fields. The electric currents and the magnetic moments of the elementary particle give rise to a magnetic field which act on other currents and magnetic moments. So the most familiar effect occurs in ferromagnetic materials which are strongly attracted by magnetic field and can be magnetized to overcome the permanent magnet, producing magnetic fields themselves. So only a few substances are ferromagnetic. The most common ones are iron, nickel and cobalt and their alloys. So the word which is used as a prefix, that is ferro. So ferro refers to iron because the permanent magnetism was first observed in lodestones, a form of natural iron ore called magnetite. So the magnetite is Fe3O4. So although ferromagnetism is responsible for most of the effects of magnetism encountered in everyday life, and all other materials are influenced in some extent or by the other by the electric or by the magnetic field by several other types of magnetism. Now, the paramagnetic substances are also there, such as aluminium and oxygen, which are weakly attracted to an applied magnetic field. So, diamagnetic substances are copper and carbon, which are weakly repelled, while antiferromagnetic materials such as chromium and spin glasses have a more complex relationship with a magnetic field. The force of a magnet on paramagnetic, diamagnetic, antiferromagnetic material is usually too weak to be felt and can be detected only by laboratory instruments. So in everyday life, these substances are often described as non-magnetic. So the magnetic state or the magnetic phase of a material depends on the temperature and other variables such as pressure and the applied magnetic field. So a material may exhibit more than one form of magnetism as these variables change. Now, let us discuss about the source of magnetism, or we can call it as magnetic moments. Magnetism in materials is crudely explained as a mutual attraction between two pieces of a material, say iron or iron ore. There are various microscopic mechanisms of magnetisms in materials which are shown later in this module. So the strength of magnetism is quantitatively judged by a quantity called magnetic moment. This magnetic moment should not be confused with the dipole moment which we know in dielectrics. So the major contribution to the net magnetic moment in materials are: first is orbital moment arising from the motion of electrons in an orbit of an atom. So the orbital moment can be related to the current flowing in a loop of a wire of zero resistance. So in short, we can say that one source of magnetism is motion of electrons in an orbit of an atom. The second is spin magnetic moment due to spinning of electrons around its own axis. And the third is nuclear magnetic moment due to nuclei, which is rather insignificant in the context of most magnetic materials of practical interest and can be neglected. The first two contributions are quite significant and contribute to most of magnetic characters of a material, while the third component, or a nuclear magnetic moment, is rather insignificant in the context of most magnetic materials of practical interest and hence neglected. Now let us discuss about the orbital moment. According to Ampere's law, when a current flows through a coil, it gives rise to a magnetic field in a direction perpendicular to the plane of the loop. The field is related to the current by H is equal to Ni, where N is the number of loops per unit length of the coil, I is the current in amperes, and H is the induced magnetic field in amperes per meter, that is A per M. So students, you can see in the figure shown that there is a coil carrying a current in some direction where the magnetic field is pointing upwards. So you can find the direction of magnetic field by the right hand rule. Now the relation for the applied magnetic field H is given as H is equal to Ni by L, where L corresponds to the length of each turn. Now here the phenomena of current and magnetic field can be reversible. So we can apply the magnetic field and there is an induced current, or there is a current in a coil, there is an induced magnetic field. Now let us see the response of a material in such magnetic field. So as we have discussed previously, there is a magnetic induction. So if there is a material, the magnetic induction will be resulted in the material. So B is the magnetic induction inside the material, which you can see in this figure. So the relation between B and H becomes B is equal to mu naught H, where mu naught is permeability and H is Ni, which we have discussed in the previous slide. The origin of magnetism. So as we have discussed in the previous slide, we discussed that there can be three origins for the moment. The first was orbital moment due to the revolution of electron. Second was the spin moment, and the third was the change in orbital moment by the changing field. So these three mechanisms you can see in the figures on the right hand side. Now students, let us calculate the expression for orbital moment. Now based on classical mechanics, the current I is nothing but the charge per unit and is expressed as I is equal to charge per unit time, that is Q by T. So the time is nothing but the circumference divided by the velocity of electrons. So that is T is 2 pi r by V. So the current becomes QV upon 2 pi r, which we will be using in this derivation, where r is the radius of the orbital. Therefore, the orbital magnetic moment, which is represented by mu m orbit, which is the product of current, that is I, and area A. So here area is pi r square and current which we have discussed is QV upon 2 pi r. So the orbital moment becomes mu m orbit is equal to E by 2m into mvr. Now, as we know that mvr is J, where J is the angular momentum. So, the expression becomes mu orbit is equal to minus E by 2m into J. Here we are using minus E because of the electron. Spin moment. So the spinning of electron about its own axis also gives rise to a moment. For a purely quantum mechanical reasons, for an electron spinning around its own axis, the ratio of spin magnetic moment to angular moment is twice as large as orbital moment. So, we can state that mu s is equal to minus E by mj. Total magnetic moment. Now, the total magnetic moment for an atom containing several atoms is basically the net sum of these two contributions, that is orbital magnetic moment and spin magnetic moment. So, mu net is equal to mu orbit plus mu net. Although it is not possible to explain classically, from quantum mechanics, the ratio of net magnetic moment to the angular momentum always works out to be between 1 and 2, related by a factor called Landé-G factor, which we denote by G, because the net moment is sum of these two and can be expressed as mu net is equal to minus G E by 2m into J, where G is the Landé-G factor and it is 1 for purely orbital moment, 2 for purely spin moment, and is 1 to 2 in the range of 1 to 2 for mixed. The Landé-G factor is mathematically given as 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by twice of J into J plus 1, where L is the orbital angular momentum, S is the spin angular momentum, and J is the total angular momentum. According to quantum mechanics, the angular moment for an electron with a characteristics number J is expressed as capital J is equal to root of J into J plus 1 times h cut. So here J is angular quantum number and according to it L is orbital moment and S is spin quantum number. For spin moment, h half will be h by 2 pi, where h is Planck's constant. Since the magnetic moment is now quantized as a result of angular momentum being quantized, for an electron, we can define a basic quantum unit of magnetic moment as Bohr's magnetron, that is mu b, which is given as mu b is equal to E h cut upon 2m. So on substituting the values of E, h cut and m, we get the value of 1 Bohr magnetron, which comes out to be 9.274 into 10 to power minus 24 amperes meter square. The nuclear magnetic moment is only of the order of 10 to power minus 3 mu b, and hence it is neglected in most cases. So the magnetic moment mu m in terms of Bohr's magnetron will be mu m is equal to minus g mu b into J, and where J is L plus S. Macroscopic view of magnetization. We will refer to the same geometry here, in which we consider a current carrying coil. We define magnetic induction as B, which is equal to mu naught H, where mu naught is magnetic permeability of vacuum, and its value is equal to 4 pi into 10 to power minus 7 henries per meter. The basic unit of B are Tesla or Weber per meter square. This also explains that while H depends only on the current, B also depends upon the medium surrounding the wire, which defines mu naught. So now, rewriting the equation, we get B is mu naught Ni. Now imagine if a magnetic material is inserted in the coil, then there is current induced in the magnetic material too, called the Ampere's current, Ig, which modifies the equation, and the magnetic field, which is mu H, becomes mu naught Ni plus mu naught Na. So here it becomes mu naught H plus M, where mu naught M is equal to Ia, where Ia is induced current due to material, capital M is the magnetization, and mu is mu naught into mu r, where mu r is relative permeability. Now, if the magnetization is assumed to be proportional to magnetization field H with proportionality constant defined by a magnetic susceptibility eta m, that is m is equal to eta m h. So we can write the equation again, and it becomes B is equal to mu naught H plus eta m h. So the final equation becomes B is mu naught mu E H, or mu naught mu R H, where mu R is the relative permeability. So here eta m, similar to dielectric materials, can be thought of a parameter which expresses magnetic response of electron in a material to the applied magnetic field and is a dimensionless quantity. So here mu r can be written as 1 plus eta m, which is the relative permeability of a material in a similar manner to that of relative dielectric permittivity. So in general, both susceptibility and permeability are tensors, and assuming that vectors are collinear, wherever there is a vector notation is not used. Classification of magnetism. Magnetic materials can be classified based on the values of magnetic susceptibility. Materials with negative susceptibility are dimagnetic, that is, eta m is less than 1. Most dimagnetic materials show very small negative susceptibility except superconductors in superconducting effect, where eta m is equal to 1, which is very useful of applications such as magnetic levitation. Materials with positive susceptibilities can either be paramagnetic, ferromagnetic, or ferrimagnetic. Susceptibility is positive but very small for paramagnetic materials and can be very large for ferro and ferrimagnetic materials. So you can see the figure on the left hand side showing the variation of susceptibility due to which the materials also changes. So for the materials where the susceptibility is greater than 0, these are ferromagnetic materials, and the examples are iron oxide, nickel iron oxide, and so on. Naturally, for vacuum, eta is 0, and however, unlike dielectric materials, eta m can acquire both positive and negative values. Now, from this slide, in continuation with the previous slide, you can see that the materials which have high susceptibility, where it is greater than 0, the ferromagnetic materials are there. And some of the examples which we have discussed earlier are iron oxide. Ferrimagnetic materials are also present, and examples are ferrite, cobalt, nickel, and so on. The second case which we have discussed, where eta is small and positive, the examples are paramagnetic materials, and the examples are aluminium, chromium, sodium, and so on. Now the next is where susceptibility is 0, that is vacuum. However, the cases where eta is very much smaller, of the order of 10 to power minus 5, in this category the examples are diamagnetic materials like Al2O3, copper, etc. So the susceptibility values of some of the common materials are provided in this figure. So students, you can see the table for the susceptibility for the common materials. So in this table on the left hand side, you can see there is a wide range of materials like bismuth, beryllium, silver, germanium, silicon, and so on. So for such materials, the value of susceptibility and permeability is given. So according to the value of susceptibility, the materials are categorized according to their types like diamagnetic, paramagnetic, or ferromagnetic materials. It should be noted also, as we will see, that except for diamagnetic materials, magnetic susceptibilities are temperature dependent. So the sign of susceptibility can also be related qualitatively to the penetration of magnetic flux inside the material. This says that for diamagnetic material, when an external field is applied, the magnetic moment that is induced in the opposite direction to the field direction, that is opposite magnetization, occurs. So this is an inherent effect present in all materials. So students, let us summarize what we have learned in this module. So students, let me recall that we have first gone through the basis of magnetism. What is magnetism? Type of magnetic material. So students, we have learned that the magnetism in materials arises due to orbital and spin magnetic moment. Then the response of a magnetic material upon the application of external magnetic field is represented by magnetic susceptibility, and the mathematical formulation has also been listed in this module. So based on spin and magnitude of susceptibility, the materials are classified into 4 categories. So first we have discussed about diamagnetic, then paramagnetic, ferromagnetic, and ferrimagnetic materials. So students, now you can judge and tell how many magnetic materials are there around us, and in everyday life also you face many magnetic materials which are present. Thank you.